Hello everyone, welcome back. Today we are going to kind of go over potential energy diagrams. So yesterday you should have watched the video with Ms. Vampus and I talking about what potential energy diagrams are. You read a Game of Thrones themed reading about them, which was super exciting. And we labeled a picture together. You guys should have labeled it. So this is just kind of practicing what you did. So this video consists of this worksheet which you're looking at right now, the extra practice, as well as the Regents practice as well. So going over this, you have a picture and questions. So let's just jump into this quickly. 1 says, which of the letters A through F in the diagram represents potential energy of the products? Remember, products are what you end with, so reactants are up front, products are towards the end. So even before we go over answers, let's, quickly label all this stuff. So A is PE of the reactants. What letter is that? E, I think, whatever this one is PE of products. F is going to be your delta H. B is your activation energy. C is your PE of activated complex. And I'm just going to say right here your activation energy for B of the forward reaction. And D represents your activation energy of the reverse reaction. So for reverse, I mean if you start at this green dot and then work backwards. Those questions are rare, but they do pop up. But if you just kind of think about it, it's okay. So, number 1, now that everything's labeled, number 1 says blah 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 blah, energy of the products. That is letter E. 2, potential energy of the activated complex. Remember that activated complex is that peak. It's that unstable intermediate thing between your products and reactants, and that is C. Number 3, which letter indicates PE of the reactants? That is A, where you are starting. 4, activation energy. So when they say activation energy, they mean the forward reaction unless they say otherwise. So we're going to put that as B. Heat of reaction, so that's the same thing as delta H. So delta H is your heat of reaction. So we spent multiple days talking about that. So if you're still confused, go back and rewatch those videos. And that is represented by F. Again, heat of reaction is the difference between the energy of the products and the reactants. Okay, so 6 is endothermic. So there are a few ways you could think about this. 1, look at where you start and look at where you end. If you end higher, that means you have to have absorbed energy along the way. That means you are endothermic. If you were to calculate the delta H values, you have to look at where you end, which is 100. So this is your heat of your products minus the heat of your reactants, which is 50. And you get a positive 50. Again, that positive number tells you it is endothermic. Okay. 7 says EA of the reverse reaction. That's that weird spot that they may ask you, maybe not. That is D. And then the heat of reaction of the reverse reaction, it's still letter F. But now, if you were to calculate it, if we're starting at the end, that means our products have 50 kilojoules. Our reactants have 100, and now you have negative 50 as your delta H value. So that makes it exothermic. So if you're looking at just the picture alone, you're exothermic if you end lower than where you started. Because you're ending lower than where you started, that means energy had to be lost or released somewhere. Okay, so now we want to put numbers to these values. Number 10, PE of the reactants of the forward reaction is 50. Products of the forward is 100. Activated complex PE is 150. activation energy. So this is again where you start to that peak. And so the peak is 150 and we're starting at 50. So your activation energy is 100. Heat of reaction to forward, we answered that in question number 6. That's 50. So again, it's the heat of your products minus the heat of your reactants, which is the same thing as the potential energy of your products minus the potential energy of your reactants. Again, your forward reaction is endothermic because you are ending higher than what you started. And then moving backwards, PE of the reactants of the reverse is 100. And the products of your reactants going backwards is 50. Your max is still 150 for number 18. Activation energy going backwards, if we're starting, again, into your peak, which is 150, minus where you're starting, so we're starting at 100. So now your activation energy is only 50 kilojoules. Heat of reaction is, like we had said in number 8, negative 50. And the reverse reaction is exothermic, because when you look at this going backwards, you end lower. Okay, so I know I went through this pretty quickly, but it is just pulling numbers off of a graph. Once you have it labeled, everything does become more kind of self-explanatory. So, other questions. What's the activation energy of the reaction? And how is energy related to the activation complex? So essentially your EA, your activation energy, is the energy needed to start a reaction. Once it has that proper amount of energy, it can then follow through with that reaction. The reaction can finish. Yesterday we had talked about pushing a giant boulder up a hill. If you don't get to the top of that hill, the boulder will come rolling right back down and you have to start over. And then how does it relate to, going back to the question, activated complex? So your EA is your activated complex energy minus your PE of your reactants. Okay. I know here it looks like it's worded really weird. The answer key on the website does have a better and neater explanation. 23, when a catalyst is used in a reaction, it speeds it up because the activation energy is lowered. So if you go back to this picture, and if you were going to add a catalyst, it doesn't change where you start. So I'm going to put this in blue. Go away. Doesn't change where you start. Doesn't change where you end. All it does is lower that peak. Kind of flattens the curve. And essentially that's why we're all staying home, to flatten the curve. Okay. 24 says draw an energy diagram, and it gave you values. So it says your PE of your reactants is 350. I think this activation energy is 100, so we need to go up to 450. And then your products is 250. So that's our max. Here's where we start. Here's where we end. So your graph should look something kind of like that, where we start at 350, we're ending at 250, and then the peak from where you start is 100 kilojoules. That's your activation energy. And again, this would be going to 25. This is, shouldn't say 24, exothermic, because your end is lower, which means energy is released. 26, how could you lower that activation energy? All we would have to do is add a catalyst. So if you're going to draw what a catalyst looks like in this picture, again, doesn't change where you start, doesn't change where you end. All it does is lower that curve. So that's it for this. Again, check yourself on the answer key that's posted if you couldn't follow along. Now let's jump to the Regents questions. And we're going to go through these pretty quickly. Hopefully it helps you. So number 1 says, how does the potential energy change when a catalyst occurs? Again, you don't change where you start, you don't change where you end. All that happens is that you lower that peak, and that's what B is showing you. Number 2, it says each interval is 10 kilojoules. So each box, every time you go up a box, you go up 10 things, 10 kilojoules. What's the activation energy? So you have to look at where you start and where the peak is. And you're going up 1, 2, 3, 4 boxes. So you're up 4 boxes. And if one box is 10 kilojoules, 4 times 10 is 40 kilojoules. That is choice C. Not super difficult. You just have to kind of do a little bit of thinking. Okay. Number 3, it says, after being ignited in a Bunsen burner flame, a piece of magnesium ribbon burns brightly, giving off heat and light. In the situation the Bunsen burner flame provides, activation energy. So fire is hot because it's giving off a lot of heat energy. The magnesium ribbon is not going to just spontaneously by itself just burst into flame and release the light. It needs that energy from the flame. Okay. Number 4 says, what happens if you add a catalyst? So again, if you even want to draw it in, it's that pink line. Oops. You start over. Only changing where you start. Don't change where you end. Only bring it down. So, arrow 4 did not change. Arrow 2 did not change. Arrow 1 changed. And arrow 3 changed. So, that is B. Again, catalysts do not affect where you start or where you end. It only lowers that peak. Okay, number 5, EA of the chemical reaction can only be decreased by a catalyst. That's a kind of very straightforward definition question. Number 6 gives you a whole bunch of words. We don't care about this at all. It says PE diagrams of reaction 1. So we kind of care about this, but not really. Without a catalyst, on the same diagram, draw a dashed line to show what a catalyst would look like. So again, we don't need really any of this. So if you're drawing a catalyst, it doesn't change where you start, doesn't change where you end, only lowers that curve. This question comes up a lot. There's only so many ways you can ask this one thing. Okay. Number 7 says dry catalyst. Again, don't change where you start, don't change where you end, just lower that curve. Okay. Number 8's a little different. It says draw a double-headed arrow. So they mean an arrow with 2 heads, like that. That's a bad one. Like that. The heat of reaction. So remember, your heat of reaction, that is your delta H, and that is your heat of your products minus the heat of your reactants. So it's this section right there. Number 9 wants you to draw the diagram, and it's saying based on this reaction. So here you have energy as a product. So if you have energy as a product, that means it was released. And if it was released, that's exothermic. And if it's exothermic, that means you end lower than where you start. So it should look something kind of like that. Make it very obvious that you're ending lower than where you started. Doesn't need to be perfect, it's just a quick sketch. Okay. Lastly, number 10 gives you a picture that we've labeled a bunch of times. It says what potential energy interval in the diagram. So essentially, what letter represents activation energy? Again, that's where you start to the peak, and that is represented by B. And again, the enter keys are posted on the Regents on the website. That's essentially it. So that is all your potential energy diagram practice. There is the elephant toothpaste worksheet you can look at. It is a really cool demo if you look at it on YouTube. That's what a lot of these science people do on like talk shows. So that could be pretty fun. There also are some at-home recipes you can use for it, but do be careful if you decide to. Bye.